Welcome to this lecture, the lecture number 6 on the third week of the machine learning course. And the topic of this lecture is logic programming. So logic programming is an abstract model of computation. In this lecture, logic programming is illustrated by the Prolog language. Other dialects of logic programming exist with slightly different properties. A logic program is an encoding of a problem in logic from which a problem solution is logically derivable. The execution of the program can be considered as a side effect of a theorem proving process. So an important concept here in logic programming is the separation of programs into their logic components and their control components, as captured by the slogan algorithm is equal to logic plus control. So essentially, the statements of logic programming represent the logic component, while the machinery of the Prolog system, in this case, as we discussed, represents the control issues. Also, a logic program can be regarded as a generalized relational database, actually, including both rules and facts. So logic programming is a computational model emanating from theorem proving in predicate logics as investigated in theoretical philosophy. A logic program is a set of axioms, and logic programming can be viewed as controlled deduction. The logic programming engine tries to find a resolution refutation of the negated query. The desired computation is a side effect of the refutation proof. The resolution method used in logic programming is called SLD resolution. So let's look a little closer to the core components of logic programming. Logic programming is based on terms and statements. Statements can be facts, rules, and queries, which are all syntactically so-called Horn clauses. Actually, facts and queries have a very similar form. They consist of a single goal. We come back to what a goal is. A fact is ended with a period, and a goal is ended by a question mark. So the discrimination here is very discrete. So I can say you can see to the right. So a fact is like father. John is the father of Tom. And a query can be X is the father of Tom. Please give me X. That's how it should be interpreted. So syntactically similar, but with a very different function. So a rule has the form A is implied by B1, B2 to Bn, where A is the head and the B's are the body. And all these, the A's and the B's, are goals. So what is a goal then? So goal. So facts, queries, and rules are statements. However, a key part of all these are goal. So goal is a compound term, and actually, compound term is a functor, which is an atom, which is a constant, followed by a set of arguments that in turn can be a term. And a term can be a compound term, of course, or a variable, or an atom, which is equivalent to a constant. So for example, in the little example to the right, you can see father is a functor, actually, but it's also an atom. John is an atom, Tom is an atom, X is a variable. Grandfather, father, parent, they are all functors. Variables is very important here because variables are used for a matching process in the computation. And variables are universally quantified within the scope of the statement. So for every statement, doesn't matter whether it's a fact or a rule, if variable is mentioned there, it's only a variable in that limited context. So a variable is not a variable in the whole set of all the statements, as it is often the case in many other programming settings. Also, statements of all kinds that have only atoms are called ground statements. They are essentially facts, or generalization of facts, and a statement with have a variable is called non-ground. So these are the basic ingredients, the basic way of expressing yourself for logic programming. So what I show you here is a slightly larger example of logic programming. And as you can see in the top, there are facts, which is essentially predicates. So the predicate male states that John is a male, Tom is a male, George is a male, Tim is a male, Anne is a female, Dana is a female, and so on. So all these are facts. And they are supposed to be, all facts are supposed to be terminated by a period. Then, so one can say that this kind of facts corresponds to features or attributes of objects. Then we have relations between objects. So as you can see in the next part, so we have facts that gives relation between those objects, and in these cases there are family relationships. And then follows different kinds of rules, more or less complex, that expresses. Some of them are simple, some of them express more complex things into several other sub-goals and so on. And then in the end, at the bottom line, you find the kind of queries you can put to a system, which has the same form of facts, but they are all followed by question mark, and they may many times involve variables. So the execution of a logic program. The idea here is to give you a flavor how this computation happens. So the execution is initiated by the user posting of a single goal called a query. You have seen an example of queries. The logic program system tries to find the solution or refutation of the negated query. If the negated query can be refuted, it follows that the query, with the appropriate variable bindings in place, is a logical consequence of the program. In that case, all generally divided bindings are reported to the user, and the query is said to have succeeded. So essentially, the computation is the indirect effect of the proof, and the result are the variable bindings. So operationally, the logic programming execution strategy can be thought of as a generalization of function calls in other languages. Because you can see that you have a query, and the query is matched to some of the goals in the set of all the rules, and there is a match. And if there is a match, that results in the invocation of the right side of the rules. So you can see this is such a recursive set of function calls. The difference is that in contrast to normal function calls, where it's totally deterministic which function is called, in this kind of language, multiple clause heads, that multiple rules can match a given call. So in that case, this kind of system makes a choice. So it takes the first rule that match the goal and dates that point and continues. So if any goal fails in the course of executing the program in the continued execution, all variable bindings that were made since the most recent choice point was made are undone. So essentially, if everything works well, then you always take the first choice in every step. But if something goes wrong along the line, you have to go back, and then you have to redo all the bindings you have made up to the point where the first point where you can take a next option. So this kind of execution strategy is called chronological backtracking. So essentially, what the prolog system does is that it tries different options. So one can see it as a search strategy through the various options that exist for this particular computation. So what does learning mean for this kind of representation? Actually, there is a specific subfield, a special subfield called inductive logic programming. It's a subfield of machine learning, where prolog statements are induced from examples. The standard logic program is used to uniformly represent both examples, hypotheses, and background knowledge. And this is a big feature. It's actually a big advantage, because in many other learning settings, you are forced to put a lot of effort on the syntax of the language in which you express your examples, the language in which you are supposed to express your hypotheses, and as thirdly, a language for expressing background knowledge. And in many cases, they are different, and there are a lot of mappings and other discussions needed to make good engineering here. So actually, the uniform language is a big advantage. So what do you input then to a inductive logic programming system? Yeah, what you input is actually the dataset, but expressed in Prolog, if this now is the language we look at, and also the relevant background knowledge. And this is pretty straightforward. The output is actually logic programming statements that newly created by the system, that entails all positive and no negative examples. Of course, logic programming as such does not really support learning, but I think what I'm argued for here is that given that some learning algorithm can be applied, logic program is a very uniform and nice framework for integrating these components in the whole system. So this was the end of this lecture. Thanks for your attention. We are now finished with the main lectures of this week. So the next lecture will be on the standard topic of tutorial for week 3.